been, but I don't wanna leave this place. There's no faith in Brooklyn.
What is going on, guys? It is your boy P, and today we're going to be looking at equilibrium constants. So recently, yesterday, I saw Mike reacting some sulfur dioxide with oxygen gas, and he got some sulfur trioxide. And so all of the reactants and the products are in the gas phase. So we call this homogeneous equilibrium, again, because they're all in the same phase. And so we define the equilibrium constant as the concentration, that's what the brackets mean, of SO3 squared over the concentration of oxygen times the concentration of sulfur dioxide squared. And now you might ask yourself where we get the exponents, and we get them from the coefficients in the reaction, or the stoichiometric factors, because we know that in the reaction 2 moles of sulfur dioxide and 1 mole of oxygen yields 2 moles of sulfur trioxide. And so we have to keep in mind the exponents in the equilibrium constant. And again, the brackets denote the activity or the concentration of each species. So what this can tell us is that if we have a system keep in mind the same temperature, whatever the concentrations are in the beginning, at equilibrium we should have the same ratio or the same equilibrium constant. So we can generalize this. So if we have any equation, so W, X, Y, and Z represent the coefficients, and A, B, C, and D represent the species, or the reactants and the products, well, we can say that the equilibrium constant is the product of all the products, or multiplying all the products divided by the multiplication of all of the reactants, raised to each power that corresponds with the coefficients in the equation. And so if we look back at our original reaction that Mike was performing the other day, we see that 2, 1, and 2 are the coefficients, or the W, X, Y, and Z's, and A, B, C, and D are the species, or SO2, O2, and SO3. And in the reaction I just showed you, there's only one product, and in the generalized form, I showed you 2 products. But we just need to keep in mind that we're multiplying all the products on one side and then dividing by the product of all the reactants on the other side. And we are looking at the concentration. That's what the subscript C denotes. Now we can also change the subscript to P, and P, it represents pressure, and so pressure is directly proportional to the number of moles according to the ideal gas law. And so instead of using concentrations, we could use partial pressures, and in order to find these pressures we could use the ideal gas law. Now let's take a look at another example. And this is called a heterogeneous equilibrium. And it's called that because each species they're not all in the same phase. We have 2 solids and a gas. So I saw Wallace the other day, and he had some calcium carbonate, and it was decomposing into some calcium oxide and carbon dioxide. And so here we have a solid decomposing into a solid and a gas, and we know that it's in equilibrium because of the arrows that are pointing in opposite directions. So we have K equals to CO2, and you might be asking yourself, what, Pete? You just told me that it's the division of the products over the division of the reactants, and you said it was all of the products over all of the reactants. Well, in calculating equilibrium constants, we need to take in mind that pure solids and pure liquids are not incorporated into the equation. So here we would think that it'd be the concentration of CO2 times the concentration of calcium oxide over the concentration of calcium carbonate. But instead, it's just the concentration of carbon dioxide, because the other 2 values cancel. And so we also have to keep in mind that all the stoichiometric coefficients here are all 1, so we don't need to raise any of them to any powers. Alright, now we're going to reverse the reaction. And when we reverse the reaction, we take the reciprocal of the initial equilibrium constant. And so in any reaction, say we're using Hess's law or something, and we need to calculate the equilibrium constant, we will take the reciprocal. And it makes sense because we divided the products over the reactants, and now we're switching the products and the reactants, so we want to flip the numerator and the denominator. So what does this tell us? Like, what do equilibrium constants tell us about a certain reaction? Well, if our equilibrium constant is greater than 1, it means that it's product favored. And so how do we get this? Well, we divided the products over the reactants, and if there are more products than reactants, then we know, well, there are more products in equilibrium, so it's product favored. But if it's less than 1, it's reactant favored. And that's because there's more reactants than products, because if we have a less than 1 ratio, that means the numerator is smaller than the denominator. So there are less products than reactants, and the reaction is reactant favored. Now we have another thing called a reaction quotient. And a reaction quotient Q is indicated by this expression. And so looking at this expression, it looks exactly like what we had with our equilibrium constant. What makes it different is that it can be described at any time during the reaction, whereas the equilibrium constant can only be described when the system is at equilibrium, hence the name. And so we can compare Q and K. If Q is less than K, then we know that some reactants must be converted to products for the reaction to reach equilibrium. And if Q, the reaction quotient again, is greater than K, then we know that some products must be converted to reactants in order to reach equilibrium. So this is the reaction quotient, and again, the equilibrium constant is just the reaction quotient at an equilibrium state. So that is it, guys. I hope you guys enjoyed this video. The more you know, guys, the better you are. Peace.